Okay, so today, so today we're going to be mostly focusing on neural networks. So that will be the main topic of conversation today. I know that, just to pick up on a couple of things from yesterday, when people were doing the practicals, I realized that for those of you who had chosen to try to do the practicals connecting to the back-end nodes on Archer, it didn't always go as smoothly as it might have done, because some of the libraries couldn't be easily downloaded directly from the internet, because the back-end nodes of Archer are not connected directly to the internet. So this is one of the it highlights a sort of real life thing that you see with many HPC systems that were not really designed in the same era or with the same kind of approach to things as what's often done in the machine learning data science community. People in data science are actually sort of quite used to being able to download data sets and things like that from the internet in the course of their analysis. It just, I think there's probably other things that we could do with Archer in the medium term to sort of help make that a little bit easier in terms of having more things pre-installed. But it is a fact of life that many supercomputers, anyway, because of the fact that they're not directly connected to the internet, there's a bit of work that has to be done to stage data and to make sure that available libraries and so on are installed before you actually run your scripts. So yeah, I'm sorry that didn't all go entirely smoothly today. If you're, my recommendation today is probably to use the front end nodes of Archer, as most of you I think were doing yesterday. I think that will make things a little smoother. In principle, there's no reason why you can't do this on the back end, but it just a few more hoops to jump through in terms of getting things installed. All right, and so today's practicals are, well, we've gone quite quickly from completely base level right up to neural networks now. So some of the practicals, particularly later in the day, it might be sort of a little bit trickier to follow along in the time that you have available. Hopefully you'll be able to follow up on these, spend a bit more time on them later after the course if you want to. Like I said yesterday, in principle, I'm happy to take questions and so on by email after the course is finished. When I'm busy, I'm not always able to respond to those straight away, but I will try and make sure I get back to them and follow up with any questions that people have on these practicals. In some cases, I think I might also be able to post some worked examples or some partial solutions to these practicals onto the repository as well. So if you're interested, that should appear soon. Okay, so I think then, are there any questions from yesterday before we make a start on today's material? Yes, Yin.
Hi, I'd like to check my understanding on classification, if that's okay.
Certainly, yes.
Yeah, so my understanding is that it class a data point based on similarity or distance, and that calculation is done during the prediction stage, right? So my question is that during the training, is there anything being done to the data?
Is there anything being done to the data?
Like
No, well,
or
yeah, no, the data itself is not transformed. The data is passed through the neural net. Sorry, onto neural networks. The data is used by the machine learning algorithm to create the model. So the data is being passed in to create the model, and it's the model really that's being updated during training. So it's the model that is being changed during training. If you can take it back to the idea of regression, your blue dots, the points that you're trying to fit the graph to, don't change during the training process. What you do is you're trying to kind of move the red line around, the line that you're trying to fit, until you find the best fit amongst the blue points. So the data itself does not change during training. It's just fixed, and that is, it's the parameters of the model that change during the training process.
I think the part that I'm a bit confused is that what exactly is the model? At least with linear regression, we can see an equation. But with this classification, what exactly is this so-called model?
Yeah, it will be. So I'll give you another example when we get onto the neural networks. But you can think of it as a complicated equation with many parameters, many thetas, as they're often, as we've referred to them so far, or many weights when we go onto neural networks. But the model ends up being a very complicated equation that, with many parameters, that takes the input x as the argument to the function and returns an output y, which is the predicted value. So the model, you can really think of the model as just a very complicated equation. For linear regression, that equation is a straight line. But for neural networks, it will be much more complicated than that. But it is ultimately just an equation which you can write out. For k-nearest neighbors, it's a little bit harder. There is an equation there. Although there is a function, well, maybe not an equation, there is a function there, because you could actually write it down in terms of the distance to all the points and so on. It would look horrendously complicated, but it is just really a function, a parameterized function that takes the input data and gives you the value that you're trying to predict. So you can replace model with function, if that helps.
Yes,
you're trying to find a hidden function that will predict the value for you.
Okay, so there's definitely some sort of like hidden mathematical function or computational algorithm that actually exists. Okay,
Exactly.
okay, yeah, that clears everything.
Yeah.
Thank you.
Aaron?
Hi, Adam. So I'm pretty much eager to know, how do we go for a precise output, like, so in terms of precision, we can say that the modeling plays a role as well as the training data. So how do one judiciously choose the model, so that the effect of the training data has less influence on the outputs, basically. Like, even with sparse data, I could be able to find a better model and get better results. And what's the importance one can attach to the type of model one can choose to get the output?
So selecting the form of your model is something that can be difficult. What you want is one that captures enough of the complexity of the situation that you're trying to capture without being too computationally complex. It is a difficult trade-off to make, and it's not always a priori obvious whether you're going to do better with logistic regression or a support vector machine or k-nearest neighbors. For many people, many problems, it's a matter of trying things out and see which works best. It's the sort of empirical aspect to this. One reason that people like neural networks is that they are so general that they can capture basically any, well, it can be shown that they can capture any function, in fact. So in principle, it's possible to find a neural network that will represent any function, and so could, given enough information, make the perfect prediction. And because computers are now, generally speaking, so fast, many people just start with a neural network. Even though it's computationally more complex. And So in terms of finding your model for classification, you can start straight away with the neural network. Now, of course, as you'll see, as we come on to today, then it becomes down to, well, what architecture of neural network do you choose? And we'll see examples today of ones that are used for image recognition, ones that are used for sequence prediction. That they've got certain features about them. So it is quite hard to. That's, I suppose, a bit of the art to it, is in knowing the kind of model that is likely to work. So in practice, it's about looking around and seeing what other people in the field have applied and to the particular problems that you're looking at, or similar problems.
Yes, correct.
And trying them out empirically.
And what matters is the fineness of the training data. That counts a lot. Right?
Yeah. So the training data is very important. Having good training data is really a prerequisite to being able to get good predictions out of your model. Without good training data, you can't really build a good model.
Yeah. Okay. Yeah. Thanks.
Okay. Thank you for those questions. Let's make a start now on the neural network stuff. So you can write whole lecture courses on neural networks. So what I'm trying to do today is to sort of pick out those things that I think are important, to give you the ideas behind them and show you how they work, so that it gives you a sort of base on which you can build. I'm hopeful that further down the line there will be a more detailed Archer course that talks about how this can be scaled up a little bit, because that's obviously where a machine like Archer would come into its own, or another kind of large machine that is built with a specific task in mind. But today I'm sort of just going to give you an introduction to the topic, but I am going to go under the hood a little bit. Rather than just tell you how to use them, I'm going to sort of show you how they work, but obviously it'll still be a bit superficial, so please bear with me. If there's other information you want me to go into more detail as I go along, do feel free to ask questions as we go. So in this talk, I'm going to give you a brief introduction to neural networks and introduce some of the terminology. Hopefully I've done some of that setup a bit already yesterday with the other machine learning things. Then I'm going to give an introduction to logistic regression, which is another kind of classification algorithm. But the idea behind that is to show you that most of the ideas from neural networks actually come from these simpler methods, and then you just build it out into a network. So then, we'll move from single neurons to networks and show how the neural networks are built up. We'll introduce something called an activation function. We'll then talk about computational graphs in general. Then we'll talk about forward and backward propagation, which is sort of information flowing in the two directions through the neural network, as you'll find out a little bit more about what these mean. So I'm going to start off with my normal selection of definitions from different people, and then I'll pick out the parts that I think are most important. So Wikipedia says a neural network is a network or circuit of biological neurons, or in a modern sense, that's the case that we're talking about here, an artificial neural network composed of artificial neurons or nodes. So picture here on the right, these circles are the neurons or nodes. Second definition, neural networks, also known as artificial neural networks or simulated neural networks, are a subset of machine learning and are at the heart of deep learning algorithms. Their name and structure are inspired by the human brain, mimicking the way that biological neurons signal to one another. So again, this I think uses the right terminology here in terms of being inspired by the human brain. The human brain is much more complex than these networks. But the idea of having nodes, of having these little circles connected to each other by edges or lines, or however you want to refer to them, this comes from a very simplified model of how the brain works. The idea that neurons in the brain fire in response to signals that come from other neurons. This is another definition. This is a bit more mathematical. A family of parametric, nonlinear, and hierarchical representation learning functions, which are massively optimized with stochastic gradient descent to encode domain knowledge, that is, domain invariances and stationarity. So this doesn't really talk about it as a network at all. It talks about it as a function, to go back to what we talked about in the introductory questions today. You can think of the model as a function which takes some input and gives an output. And what you're trying to do when you build your model, when you learn your model, you're learning the hidden function that transforms the input to the output. I'm saying you learn the function, what you don't, well, I mean, you could write it down, the output that you get in terms of all of the weights, but you don't ever really think of it as the function being written out in terms of mathematics that you find. You just find the values associated with all of these edges, really. I'll come on to that in more detail. So these are some definitions of a neural network. You can really just think of it as something like this. There's nodes and edges. So it's a network. And the idea is going to be that we set up this network in such a way that when we put in the values of our features, it can make a prediction for the hidden feature that we don't know yet. So neural networks are made up of layers. In this, where they're made up of these little things called the neurons, which have inputs, which are normally shown coming in from the left, and outputs coming out from the right. And then these neurons are then arranged in layers. We have the input layer, which is depicted on the left normally, and an output layer on the right. Normally, in most conventions, input layers tend to be labeled as layer 0. And then we have a hidden layer and an output layer at the end. What we can do is add as many hidden layers as we want into our neural network. And as you'll see further down, the more layers we add, the deeper this network becomes. And this is really the only thing that the only thing behind what makes a neural network deep is that it has many layers. So it's talking about having many layers. You can also, of course, change the size, the number of neurons in each layer, but the depth means that you could have layer 1 hidden layer, layer 2 hidden layer, layer 3 hidden layer, layer 4 hidden layer, and an output layer at the end. Yes, Aaron?
Oh, that's my old one, sorry.
Okay, sorry. No, Sam, yeah, did you have, oh, and Stephanie, I see your hands are up. I'll take Sam first, just because he's at the top of my list.
Hiya. So yesterday we were learning about parameters, right? And when you look at examples of neural networks, especially of like large language models, they have like 7 billion parameters or whatever. What are those parameters here? Are they the nodes, or are they the connections between the nodes?
I'll go into this in more detail in a bit, but they are the connections between the nodes. So the weights are associated with the edges. They're called, in neural network speak, people talk about weights more frequently than parameters, but these are exactly interchangeable. So all the parameters are associated with the edges. I'll come on to that in a bit more detail. Stephanie?
So my question is, does every node has to be connected to each node in the next layer, or is there an option to kind of have paths, or?
another very good question, and I'll come back to that again later on.
Okay.
So we're going to start with the simplest case, which is a fully connected model, which historically, chronologically, is also how things started. The original ones always had fully connected layers, which means every node in one layer is connected to every node in the next layer. But you don't have to do that, and we'll talk about that when we come to different architectures of neural networks.
Okay. Thank you.
So yeah, this is the starting point, and then we can sort of build out some complexity from here. So a deep neural network is simply a neural network with many hidden layers. So again, in this case, it's also still shown as fully connected to start with. Doesn't have to be, but what we have here is still have a single input layer. This output layer has two different outputs shown here with one, as we'll come on to when we're showing the different kind of things that can appear at an output. You can get different numbers of things in the output layer. Often there's sort of different ways of doing this, but when you're doing maybe a regression and you're looking for a single value to come out, you quite often have a single node at the end in your output layer. Normally, when you're doing classification, what we have is an output here in the output layer, one for each possible class that you could select from, and you're picking the highest value. In some architectures, actually, what you can actually you might get that the number of that class or something directly output in the output layer, but it's quite common to have one output here for each possible class that your model could predict, and the one that you're actually predicting is the one with the highest value that we'll look at. So deep learning is simply machine learning using deeper networks. Some people are now using deep learning and neural networks almost synonymously, because now most of the neural networks that we use are quite deep. It turns out that, so originally to go deep was computationally too expensive, but now we have the computational power to evaluate all of these layers. And it turns out that having the deep layers allows these models to capture the complexity of the kind of systems that we're trying to predict, and it works. They work very well. So just a reminder of what we were talking about yesterday, that deep learning is an important part, but not all of neural networks. Neural networks are used for machine learning and AI. What we did yesterday was this bit of the yellow sticking out. Or actually, what we did is the yellow that's not inside the blue circle. So there are plenty of machine learning algorithms that are not neural networks, but these days the most important ones, are the deep neural networks. So in terms of a hierarchy then, so we have neural networks. They can be sort of split down maybe into simple neural networks and deep neural networks. These deep neural networks then can be further subdivided into things like you might have heard of convolutional neural networks, which we'll come back to in the second lecture today. Recurrent neural networks, which I'll mention briefly, but won't have the chance to go into in great detail. And then other things that build on these recurrent neural networks, like transformers, the networks that are behind ChatGPT and things like that. So we have the two kind of most important things that we want to understand how they work for neural networks is the training and the predicting. How do we build our model? Then how do we use it to make a prediction? So when we train, just like in the cases we had yesterday, we had labeled data. So we had a certain part of our data set with inputs, and known outputs that we're going to use to train our model. So the training data is used to train the model on both sides, and I'll show how that's done. And then once we have built our model, trained the model, we can take unseen data, put it in at this side, and we get a prediction out at the end. I use the word prediction. It can also, it doesn't have to be sort of in the future. It could be that, are you predicting whether the image that you put in is a cat or a dog? I mean, you know, you're trying to infer something about the data from the unseen data. And in terms of the flow of information, the flow of the numbers, the flow of the data through the neural network, the training bit, I think we mentioned yesterday that training is computationally more expensive than predicting on the whole. And that's because with training, we pass information, pass data backwards and forwards through this network to train it. We repeatedly send things forward. We compare them to the output that we get here, and then we go backwards, and then again we put in a bit more data or the same data again, and we compare it to the output that we get, and we move it backwards. So this is a sort of iterative, repetitive process, just like using something like stochastic gradient descent with linear regression, that you're trying out different slopes, you're trying out different parameters in order that you can best match the output that you get to the input here. So this is a back and forward process. With the predicting, once you've got your weights, your parameters on these edges, it's just a one-way pass through the network. So at this point, once you've trained the network is fixed, and then you just put in some unseen data and get a prediction out at the other side. So now, before we go on and talk a little bit about this training process, let's take a step back and go away from neural networks again, back into a certain kind of classification. So yesterday we looked at k nearest neighbors. Today we're going to look at heuristic regression, which is often used when you're doing binary classification. So here's some kind of motivating example. Each of these blue dots represents a student, or each of the blue and orange dots represents a student. The students put in different amount of revision for their exams. Unfortunately, all of these students failed the exam. These ones passed it. So we're not in this case showing a grade or anything like that. We've just got information on whether the students passed or failed. What we can see is that it looks like there's some kind of relationship here, that people who put in fewer hours of revision tended not to do so well. People who put in the most revision tended to do better and passed. But of course, there is sort of an overlap here. Some people unfortunately put in a lot of revision, but just didn't have what it takes to pass the exam. Others were a bit luckier, or a bit maybe have the prerequisite knowledge or something. They didn't revise very much, but they still passed. So it's not a strict relationship. Above a certain amount of hours of revision, they will pass. So what we want to do is come up with some kind of model that will kind of predict, given the number of hours that you put in, are you likely to fail or are you likely to pass? Now, one thing that you could do is go back and put in, we'll just fit a straight line to these dots like we did yesterday. We'll do linear regression and we can see what that predicts. Well, it might give you some predictive power here, actually, in this simple case, but it's not ideal for multiple reasons. For a start, you've got to sort of interpret what this line means if it was to go below 0 or above 1, or indeed all of these values in between. If you get a prediction that somebody is 0.4, does that mean they pass or fail? Now, you could put in a threshold and do it that way, but it's not an ideal. You can see yourself that that line does not look a particularly good fit to that data. So another thing that we could do is fit a graph that looks something like this. Instead of trying to predict whether a student will pass or fail, what we want to do is to come up with a probability of passing the exam given the number of hours of study that they put in. And you can see that a graph that looks a little bit like this in some ways represents the data better. For the ones down at this end, you can be pretty sure that they're not going to pass. The ones up at this end, you can be pretty sure that they will pass. So the advantage of this kind of shape, there are different graphs of this shape that you could come up with. You can also, for a certain very specific set of mathematical problems, sort of binomial selecting from two classes, you can also kind of come up with this function from first principles. But actually, historically, really, that's not what happened. People looked for a function that had roughly the right shape and tried it out in these classifiers. And what they were looking for is something that was often close to 0 or 1. It never went outside the range 0 to 1, and it could give you a value for any of the values predicted. The shape of this function is called the logistic function, and it has the form 1 over 1 plus e to the minus z. It's often written with a z. I don't, well, I can maybe explain why later on, but if this is the normal x-axis, you can think of this as e to the minus x here. So that's the shape of the logistic function. But how do we sort of in this case, we've only got one, but we've only got one feature that we are basing our prediction on. So what happens if we have multiple features that we want to make our prediction on? Well, we can arrange all of our parameters like this. We can come up with something theta naught x naught plus theta 1 x1 plus theta 2 x2. So now we have multiple parameters, and then we define z, the thing that we're going to put into this shape here, as the dot product of the theta vector and the x vector. So we end up with something like this, or written concisely like this. So now for any number of parameters, we can come up with a value of z and plug it into this formula. So incidentally, logistic regression is part of a family of what are called generalized linear models. Why are they still considered linear when they have this shape here? It's because the z is a linear function of the parameters and the x's. So that's not really too important, but what is important is how you calculate z from the parameters and the data points. And then we're going to classify as 1. We're going to classify as true in this binary classification, or passing the exam, if this function f of z is greater than 0.5. So working this, what does that actually mean in terms of the parameters? Well, this is just going through step by step, writing it out and rearranging the formula. There's no magic here. But if we solve this, going through step by step, what we end up with is that we will classify as 1 if and only if this equation ends up being greater than 0. In other words, what we have here is the equation of a hyperplane in many directions. So it's a line in two dimensions, a plane in 3 dimensions, and a hyperplane in a number of dimensions. But you've got some kind of hyperplane that can separate your data out. And if you're on one side of that hyperplane, you're classifying as pass, and on the other side as fail. So logistic regression, this simple case, can only deal with linearly separable data sets. So you could imagine points here on one side are classified as one class, points on the other side of the hyperplane are classified as the other class. And these data sets are nicely linearly separable, which means I can put a line in between them or a hyperplane in between them in a large number of dimensions and say that all the points on one side belong to one class and all the points on the other side belong to another. That's not true in general, which is why logistic regression tends to only work in simpler classification cases. Another thing that we do with linear regression, logistic regression, is that when we're finding that line, that dividing line, we need a cost function, just like we did for linear regression. This was the one we used for linear regression. For logistic regression, we have one that looks quite a bit more complicated. Where does it come from? Well, you can derive this expression for a cost function under certain specific conditions, making the assumption that the data are independent and identically distributed. In practice, it can be used more generally. So again, there is this expression came from probability theory originally, but it had the right shape, it had the right features of going to, again, you're looking for a cost function where y gets close to f of x. You want this to be low, and that's, you can show for this expression as well, that when by rearranging it, that when yi gets very close to f of xi, this thing goes to 0. So just a quick reminder about gradient descent with one parameter, what we had yesterday, that the aim is to find that we're minimizing a cost function by moving along a slope until we can find the value of the parameters that minimize the cost function. So that's how logistic regression is built up. But what bits of that carry over to how a neural network is built and trained and used? So when we construct the neural network, we decide on the architecture of the network. How many layers that we want in our network, and how the layers are connected. And finally, the choice of activation function. Well, what do I mean by activation function? Well, in logistic regression, this is our example of the activation function. So it's the thing that takes all of the inputs coming in, all of the parameters on the edges of the that are coming into a node, and comes up with a single value z. So we'll see that shortly. So yeah, we have to decide on the architecture, how many layers, how the layers are connected, and the choice of activation function. Our weights are then initialized. That's equivalent to picking your initial straight line in linear regression. Can be at random. Sometimes they're normally initialized at random. And then we train the neural network, which is a repetitive, iterative process, remember, back and forth through the network. So we feed the data into the neural network. We make a forward pass. So we make a prediction based on the current weights, and we calculate the cost function, analogously to how we calculated the cost function in linear regression. And then we do a backward pass, which is sometimes called back propagation, to find the derivative of the cost function. And then we update the weights and biases using the derivatives that you've calculated. So this approach is just exactly the gradient descent optimization algorithm again. I mean, whether it's precisely gradient descent or some variant of the optimization algorithm that uses the gradients, this is just exactly the same as what we used as an example for linear regression or logistic regression. And then to do a prediction, we do a single pass through the network. So we've still got gradient descent and cost function that we had in the linear regression example. We're adding in this new concept of an activation function, which is also used in logistic regression. It's a way of taking all the values and coming up with a single value that helps to that can be passed onwards through the network. So the next few slides is based on an approach to teaching neural networks, which I've picked up mostly from Andrew, and I think it's a nice way of explaining it. It's also inspired by some of the lectures given in the past here and elsewhere at the University of Edinburgh. But I wanted to give some credit to Andrew for his explanation, which I quite like here. So let's go back and build this up and all the pieces that we've talked about so far. So this is our neuron. On this side, we're going to calculate some value z, which is made up of the x's. So we're just like before in the logistic regression example. We're going to write our thetas now as w's, just because that's the common notation used in a lot of neural network literature. And we're going to have this other thing, our theta naught, our theta zero, the constant element, is normally explicitly represented by something here called a bias. The bias is a feature of the node. So the weights can be associated with the edges. The bias is a feature of the neuron. Normally, well, no, okay, the bias is a feature of the neuron. So, so the first thing that happens in one of these neurons when the data flows in is that we calculate the value of z. And then to the value of z, we apply an activation function, which is often, but not exclusively, the logistic function that we just talked about for logistic regression. So it's the same function, 1 over 1 plus e to the minus z. And the value that you get out there is that output A. So why is it called an activation function? the idea is that, so again, inspired by the human brain, that the neuron activates if it gets the right signals coming into it. And so the neuron is either basically on or basically off. So most of the activation functions are chosen to have this feature where they, just like that, the graph of logistic regression, from many values, it's either close to 0 or close to 1. So you get a clear distinction coming out from your activation function. Yes, Sam?
Is there any constraint on the weights that are going into any of these neurons or nodes, whatever you want to call them? So like here you have W1, 2, and 3. Do they all have to, if you add them up, do they have to be less than 1, for example? Are they like probabilities, or is there no restriction on them?
They're not probabilities, but the values themselves, sorry, I should have said that. The values themselves will ultimately be between 0 and 1.
Okay.
Because the output of, as you go further through the network, that's maybe more obvious, because the output of an activation function is chosen as with logistic regression. So everything that you always get out, no matter what input that you put in, will always be between 0 and 1. So yes, you could imagine that you could initialize the weights to anything, and then they would go back to being between 0 and 1, but they're normally initialized between 0 and 1 as well. So yeah, the constraint on the weights is that their values between 0 and 1. Stephanie?
Can the activation function, which here is a continuous function, can this also be a discontinuous function? Say, okay, we say it's 1 if z is larger than 0, and 0 if z is equal or less than 0?
So I think you're leading me on to my next slide.
I'm sorry.
That's okay. That's okay. The answer is that there are various different common activation functions. So the one that we've talked about so far is the sigmoid. People at different points in time have used the tanh function. They've used ReLU, which is shown to work well in certain conditions. So this is it's a continuous function, but not differentiable everywhere. So it does have a discontinuity here in the derivative. So it goes from being flat. You can, and other ones people use are called leaky ReLU, which is a bit like a ReLU, but does have some slope here. The max out is a little bit harder to depict as a single graph because it depends on multiple weights coming in. And then this is another one. So the ones that probably end up being some of the most common now, ReLU, partly because of its simplicity here, it makes it computationally very quick to calculate rather than actually doing this, working out this one actually works quite well. So I'm just trying to remember, so in this case, can it, maybe the weights with the ReLU are not constrained between 0 and 1. I think that's true. So I think there can be any value of the weights. So I think the constraint on the weight is only there if it comes from whichever activation function that you use, to go back to. It was your question, Sam. So I've jumped ahead of myself a bit without really thinking it through, that there are some activation functions that don't restrict you to a value between 0 and 1. Okay, so yes, again, this is a choice in the architecture of the neural network. What do you pick as your activation function? And again, sort of some of these have been found to be better in certain circumstances than others. Sigmoid was one of the sort of earliest ones used kind of by analogy with logistic regression, but these ones have been found to work well in practice. I seem to remember that if you go back and again, historically, the very first sort of neural networks had used a step function, which really was effectively discontinuous around 0. It was either -1 or 1, but computationally that proves difficult, because one of the things that you want to be able to do, as we'll see in a minute, is to take derivatives, and whilst we can handle cases like this, to have a complete discontinuity makes it difficult to handle derivatives. So yeah, originally there are different shapes of activation functions, and probably the one that you'll actually see most often in practice is this ReLU one. So now let's leave neural networks aside for a moment and think of some very simple problems to show you a little bit to show you how propagation works in neural networks. So imagine that we had some equation. We were trying to find Z, and we knew that the answer was 3a plus 2bc. One of the ways that you could work out this is to break this down and to say, well, Z is something plus something else. It's something plus something else. And then we can say that that first something is the 3a, the second something is the 2bc. And so we break it down into pieces of the calculation. And then we can depict that using some kind of a graph. So we could say that, okay, we're trying to calculate Z from A, B, and C. And the way we do this is, well, first of all, we multiply A by 3, and we multiply B and C together and multiply them by 2. And then we take those two answers and then we combine them and calculate Z by adding these things together. So you can think of any kind of calculation that you might want to do, any function that takes inputs and gives an output, as being something that you can represent as a graph that breaks down the calculation into something that happens bit by bit. So we'll come back to that computational graph in a moment, because you'll already see that it's starting to look a little bit like a neural network, hopefully. So this is just a reminder of the neuron with the activation function, and we calculate these are just sort of the steps of the calculation that are performed when we do forward propagation. It's written in matrix notation in the same way that we did with the linear regression with multiple features yesterday, just to keep it succinct. But the colors are here represent the colors of the layers. So what it's saying is that we, first of all, when we're doing forward propagation, we calculate the Zs, first of all, this part of the calculation, the left-hand side of the blue neurons here, using W1, they're the weights coming into here. So that one, 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 that one. Multiply them by the X's. So that's the values that came through these X. So that's the outputs from, this is, the values of X are the values that came out of these nodes here, the input layer. So they are just the original, it's the input data. It is exactly the input data, which is why I've used X here. So the input data goes, it's multiplied by the weights of the edges, and that's used to calculate the z's for the next layer. And then you also add the biases associated with the neurons in this layer. Then you apply the activation function, which I'm using G here as a general, it could be a general function, so it could be any of the activation functions that we saw on the previous slide. And that gives us the activation A1 coming out of this hidden layer. And then we just do this repeatedly for all of the layers. And so the next layer is calculated in the same way as the first one. But now instead of having the X values in, we use the values here that come out of here as the input to here. So we just go through the graph, forward propagation. At each stage, we multiply the incoming data by the weights, add the biases, and then perform the activation function. So we do that repeatedly until we get a value out at the end, shown here as A2, which is the value in our final final neuron. So by the time we reach the end, we have calculated our y hat, our predicted value, and using just the y hat, the predicted y, and the y, the known label from our training data, we can calculate the loss. Whatever our loss function is, we can use the y that we've just predicted and the y that we know from our training data, and we can calculate the loss function. So that's good. But the next thing we have to do, so that we can do gradient descent, is remember, we know the value on the point, but we also need to know the slope at that point in the graph, so we can do gradient descent. We need to know the derivative of the loss function with respect to the input values. So we need, the loss function was very easy to calculate because it's based just on this side. But for the gradients, we now need to work out d loss by d input 1 and d loss by d input 2 and so on. So this is where back propagation comes in. Yes, Yin?
If I remember correctly, in the derivative for linear regression is over d theta, which is the parameter. But over here, we are doing a derivative over x, which is the input instead of the bias or weight.
That is a good question. Is my knowledge actually breaking down? It was by d theta. Sorry, checking on the loss function. Yeah, so loss function is basically the same as the cost function. Okay, I should have maybe been a bit more formal about that. Normally, the cost function is defined for a particular point, and the loss function is adding up the cost function for all of the points, but they're effectively the same thing. To go back to the derivatives, okay, maybe we should not really make a direct comparison here, but I'm going to have to think about that one, I think. I might back after the break. You can think of the loss function as the sum of the cost function for each input. Yes. Great. I think we do want dx's. That's a very good question, comparing it to the thetas. I think this probably, maybe sort of, it's a breakdown in my analogy. I'm going to have to think about that a little bit and come back to you. But but for just now, the thing that what we're trying to say is, given a small change in the inputs, how does that affect the loss function? Because we're trying to select the input that matches so we're trying to that question has knocked me a bit. It's a very good question. I'm going to go through these slides, and then I'm going to have a think about it offline at the break, and I'll come back and explain what I mean here. But for just now, let's assume that we're trying to calculate these derivatives. And the idea is that we do this using the computational graph. Because if we were to try to work out what the partial derivative of j with respect to a, this is just, we do this with the chain rule that we learned back in high school to do derivatives of a function of a function. So to calculate dj by dA, it's just dj by dv multiplied by dv by dA, and so on. dj by dB is dj by dv multiplied by dv by du multiplied by du by dB. So in the back propagation stage, what we're doing is calculating the derivatives at each step. So yeah, how am I doing for time? I'm a little bit over already. So let me, I'm going to come to the end of these slides, make a few last general points. We'll have a short break, and then I'll come back with another comment on what's going on with those derivatives. So there are different ways to train the model. Once you have the idea of a neural network and a way to perform forward propagation and back propagation, you can create then variations of this approach. So how you use your training set. So again, these are very similar to the same optimization algorithms, I suppose, that we talked about yesterday. You can do batch gradient descent, which is feeding in all of the data every time. You can feed it in batches and sort of take a random subset of your input data and feed that in each time. Or you can select random instances at random for each propagation. So that's so for this case, you can do every time you try to improve your weights, every time you go forwards through the graph, you don't always have to put in all of the input data. You can put in some of it. So these are the different variations that we have. There was a question from you, Sam.
I might have missed this yesterday. So when we're doing the gradient descent, are you updating all of the parameters and then feeding it through the next forward propagation, or are you doing it like one at a time? Because both of those, well, if there's only one minimum, then it won't matter. But if there's, again, like I said yesterday, there's multiple minimums, then it does matter. So is there...
You do it simultaneously. You update all of the weights simultaneously. That as one big matrix calculation is how it's done in practice. So,
is that just because computers like that?
Is it just because computers like that? I think so.
Like doing matrix calculations, and so that's the
way to do it.
It's faster.
And I suppose there's no. Yeah, I think that's just how neural networks are normally used. I don't know whether what would happen if you tried to update single weights at a time. So I know. So what you can. So there are sort of more advanced techniques that are used in some parts of transfer learning. The idea of transfer learning is that you train a neural network, and then, like maybe you're trying to identify something very specific, like different sea creatures on the seabed from images that have been taken by a survey ship or something, and you've got very little training data. So one thing you can do with transfer learning is that you first build a neural network that is sort of quite good at classifying similar type things like animals, for example, and you would train that on a general training set. And transfer learning means that you don't start from a completely random neural network. You start from an existing one, and you use that. Then you retrain that on your specific data to get it to work on your specific case of just these rare seabed creatures or something. And that's one way of, it turns out that works quite well as a way of doing neural network classification when you've only got a limited input set, is that you pre-train the model on more general data, and then you use specific data to train it for your particular use case. And there are two different ways that you can do that. One of them, and variations on them, but essentially you can either just take your network and continue to train it on the new kind of data. The other way is to freeze some of the weights as they are, and you no longer allow them to change. And then you put a new part of the neural network on the end, often called a head, and you use the part of the network that you've already pre-trained, but you keep it locked, frozen, and then you can just change the weights in the last part in the head to adapt it for your new problem. And then there's different variations in between where you can freeze some nodes and not other nodes. So there are variations on this where you don't train all of the weights simultaneously. But the standard that you start from is to train all the weights simultaneously. There's a comment. So there was a comment on loss and cost function. Some sources say they're synonymous. Some say a cost function is the average over the loss function, which is the opposite way around from the way I would use it. Loss function is usually a function defined on a data point. Cost function is more general. It might be the sum of the loss function. Okay, so there does seem to be some some discrepancy on how these terms are used, but maybe. So I suppose as long as you're aware of the conception, the fact that they're closely related, because they're so closely related, you can see why people sometimes use them interchangeably. But there are these two distinct ideas. One is what the function that you actually use to measure for one particular point, and the other is how they're combined. Yeah, just be aware of how the terms are being used exactly. For the backward propagation, you calculate the back propagation each iteration for a specific set of input-output values. So it would make sense that the derivative is based on the weights, as the input value would be constant in this step. Okay, I'm going to come back to you on that one, Stephanie, when I've checked a couple of things. So yeah, just running a little bit late already, so let me just finish these last couple of slides. So the neural networks one of the things that's great about them is that they can represent any function. If you want a nice visual proof of this, just to convince yourself that why this might be the case, I can recommend looking at this, which should be freely available online. Again, it's not a rigorous mathematical proof that you can represent every function, but it's a convincing visual proof. They call it a visual proof. It shows how you can, in theory, represent any function with a neural network. So some of this has already been picked up in some questions, but this sort of slide leads on to the directions that will go next. How can you build from this sort of simple? How can you build from this simple neural network where it's fully connected and everything flows just backwards and forwards into other more complicated things? So what happens if we have nodes that aren't fully connected to every node in the previous layer? One thing you can do is to create layers where nodes in layer I depend only on nearby nodes in the previous layer. And if these nodes are then used to represent pixels or parts of an image, this means you can look for what are effectively localized features in images, because you're finding bits where pixels are related to their neighbors. This turns out to be useful for image classification, and this motivates the use of convolutional neural networks that we'll talk about next. One other thing that you might imagine that you might want to do, what if we allow some connections that skip layers? That is done in some cases, and these are called residual connections, and they can create residual networks. So again, you may have heard of ResNet as an example of, I think it was also used for image classification originally. But the other thing that ResNet helps do is maintain some kind of memory of the earlier features, so you don't lose them as you go through a deep neural network. I think it also helps with one of the things that can happen. We haven't really got time to go into the details. The derivatives that you're calculating, they can, if they get they can either disappear or blow up. If they get very close to zero or become very large through the iterative process, it's computationally difficult to handle them, and it makes these things hard to converge. So it turns out that putting in some residual connections can help with that as well. Another thing that you can do is have edges between nodes that feed back into earlier nodes. So you get sort of loops in your networks. This makes doing the sums in back propagation a little bit trickier, but it's still possible. This is the idea behind recurrent neural networks, which are used for for example, sequence prediction for natural language processing. So that's useful when you're continuing to put in new elements of the sequence, new words in your sentence or something, and you want to have memory of what's happened before with the previous words in the sentence. So that slight variation of having backward links in the network is what recurrent neural networks are. So these are variations on the architectures where you have your links, how many of them you have, whether they skip layers, whether they go backwards. But the principles behind forward propagation and backward propagation and the training of all of these models with the derivatives is the same in all of these cases. So once you've got the idea of doing forward propagation to calculate values and backward propagation to calculate derivatives, that holds true for CNNs, for residual networks, and for recurrent neural networks as well. So, okay, let's take a short break now. What time are we at? We were due to break. Oh no, we were meant to have a practical first before the break. Okay, let's right. Let's move on to the practical for. But we'll stop that at 11 o'clock, like we were originally going to for the break, and then after the break, there was another practical anyway, so we'll just extend maybe the practical sessions after the break very slightly, to give time to go through the whole parts 1 and part 2. But let's start the simple neural network practical now. The first practical 8A, is using scikit-learn, just like we did yesterday. It also has an example of sort of building things up from scratch in NumPy, so doing it yourself. So just like one of the examples yesterday showed how to do my k-means, it had an implementation of k-means to show how it works. Here as well, we have an implementation of how a simple neural network works, or could be built up from NumPy. In practice, what you would use is a library like scikit-learn, or one of the sort of maybe the more production ones, PyTorch or TensorFlow, which we'll give an example of PyTorch later on. But this is, again, it's a library showing you how you can do it with scikit-learn, and an example of NumPy of a little bit of how you could kind of build this up yourself if you wanted to write your own one to see how it works. Okay, so you can work on that in the notebook in the same way that we did yesterday.
In the previous video, we talked about a cost function for the, concretely taking the example and y as vectors in this A3, where A is a term for the output layer, alphabet delta. Next, we're going to use the output label yi from the of the cost function with respect to each of your parameters. And so you can use those in either gradient descent or in one of the advanced optimization algorithms. So that's the backpropagation algorithm and how you compute derivatives of your cost function for a neural network, which is a pair xy. I'm not going to write these things, theta superscript L subscript ij, that's a real number. And so these are the partial derivative terms we need to compute. In order to
Okay, quickly then, I'm going to have another go at explaining this slide. Thank you, Robert, and I needed to take a moment to step back. I had made a mistake when I was creating the slide, and the question was spot on, and it is exactly very good observation, because the analogy I want to make is, yes, it is exactly like what we were doing yesterday with linear regression. That what we're trying to do here is to find the right weights that minimize the model. We're trying to find the values of the weights that will minimize the loss function. And that includes all of the weights as you go back through the model, right to the ones at the start. So the principle is the same, that we need to find the loss function as it's a derivative of something with respect to something far back in the network. It's not the input values, it's not the x. These are fixed, just like you said. These are fixed for a given input. So this derivative here should say the loss function with respect to the weights. So we're trying to calculate so everything else I said is correct. The loss function is easy to calculate. because you can base it just on things at the right-hand side. But we are trying to fix all of the weights throughout the whole graph, because we need all of these. And to get at the earlier weights, we need to move backwards. This is maybe at slightly the high level because it's only on the computational graph, but the principle holds exactly the same way. That the way we need to calculate the weights over here, we need the derivative with respect to the weights over here, and to calculate the derivative with respect to the weights over here, we need to calculate the derivative with respect to the weights over here. So I've just tried to zip through it too quickly, but the idea is that you can work backwards through the neural network, working out the derivative of the cost function with respect to the weights, and you have to do that at each layer, and that's why you're propagating backwards, and that's what's going on. So you're quite right. Yesterday it was by the derivative with respect to theta, and that is still true. In this case, in the neural network, it's the derivative with respect to the weights W. Fit doesn't converge. Run into the issue that the fit doesn't converge in CLF fit. Also here. Right, let me try that. To reconnect from yesterday. So thank you to those commenting in the chat. I've got to step away for 15 minutes just now. But I'll follow up on the questions on the practical when I come back at 11:15. I suggest you take a short break at some point yourself as well, stretch your legs, and we carry on at 11:15. We'll have some time to look into what's going on in the practical. Thank you. Okay, I'm back. So I can see that some people have made some progress with things. Looks like some useful comments in the sidebar. I'm going to have a little go at stepping through that now myself to see what's going on, and I can maybe make some comments as I go through. So So in terms of timings, we'll work on the practicals, but the simple neural network part 1 and part 2, we'll do that until 12 o'clock, I think, and then I'll do the last part of the lecture. So Ian, thank you for your question. I'll just get down to that point and then I'll try to clarify. So yeah, the default values in the practical are giving a neural network that a fitting process that doesn't completely converge. Yeah, so Stephanie, you solved it by increasing the number of iterations, which was one of the suggestions in the error message. So that's the right thing to do, I think. You can also change the learning rate, and those who've made it work with the changing alpha. In fact, I'm not sure alpha is strictly a learning rate here, but it's a similar concept as something, a hyperparameter. That's fine. So you're correct that even when it didn't quite converge, it was still giving a pretty good score on the test data. This is another example of where sometimes with the neural networks, if you don't always have to worry about the convergence of a specific algorithm. If at the end of the day you've managed to create a model which is giving a test accuracy of 99%, in many cases that might be perfectly adequate, but as you've seen, you've been able to fix the convergence by increasing the number of iterations to allow it to converge. So the next question, we're asked to list classification probabilities. So one of the things, so just as a general example of something that you can do, you haven't been explicitly told how to do that, but so you've seen how to do predict. One of the ways you can see other possible methods is if you start typing. Yeah, so it says, like the hint says, type CLF dot, then double hit tab. So if you double hit tab, you get a list of possible methods that you could choose. Now, for details, you'd probably have to look at the documentation, but since you're trying to find the classification probabilities, I think what it's leading you towards is to look for something, a method that relates to probabilities. So you might guess that it's predict proba, and if you want to find out more about that, you can look at the documentation by putting a question mark before it. And it does say it provides probability estimates, and it takes X as its input, and it returns the probabilities Y prob. So I think we have got, yeah, we've got X. So what it's asking you to do is this. I'm seeing if I can interpret those numbers. So I think there is, so there's two different ways you could address to do the accuracy, precision, and F1 score. So some of them are in what have we imported so far? From sklearn metrics, import confusion matrix. So in
You're currently not sharing your screen if you're trying
I'm
to.
not sharing the screen, thank you. Sorry, just typing away
No worries.
myself. So you can either calculate them yourself from the confusion matrix according to the slide that we had yesterday on the metrics for accuracy. So that you can calculate them from scratch, but you can also, there should be something in sklearn.metrics. I'm just going to import the whole thing and then we can have a look. Import sklearn.metrics as skn. And then what do we have? Double tab. So there's accuracy score. That looks promising for accuracy. Let's check them. I spelled it
You
wrong.
need to import it before.
I thought it
Can you go backwards with the import?
Yeah, well, it remembers this. It should remember the state, but obviously, no, it didn't. Okay. Right. So accuracy score wants y true and y predicted. Have I calculated those already? So the true ones are y test. And the predicted ones are, what did we label them? I should label them. What have I done wrong? 500. $500. Because I should only be predicting on the test set. That's why. So it's definitely just to pick up on your question before. So either you can calculate them, the metrics from scratch, from the values of the confusion matrix using the equations in the slide yesterday, or you can, there are built-in functions in scikit-learn metrics, which give you the scores that you need. So Yin and John, yes, it's interesting that you didn't encounter the convergence problem with the default values. Are you running on Archer, Yin, or are you running on something else? Yes, Yin?
No, I'm running it locally on my computer because I had some problem. Yeah.
Yeah, so I don't know whether it, so it looks like even though the values are seeded, like John says, it looks like there is something that's subtly different. It may be that you've got very slightly different versions of the of one of the libraries or something, which means that it's done something slightly different. I suspect that whoever created this practical originally was the one that I picked up and thought would be useful for this course. But I think that probably whoever ran it originally, they didn't see the convergence problem either. So I think it might be just down to the platform or the slightly different version. Either way, I don't think it's the actual main point of what we're trying to look at here. But it's good actually that people saw the error and were able to get around it. So it's probably the fact that it's different machines, yes, and it will be the fact that it probably is the randomness behaving differently on the different machines, but it may also be slightly different versions of the libraries that you have installed. No, in this case, populating the model at the moment is just the initialized weights and biases. So it's just putting the W1, B1, and so on into the right parts of the model.
Isn't that the line above where I have the dictionary?
Okay,
where I set it.
Oh, you see, define it here and populate the model. I think maybe it's just splitting it into two parts. I think it just wants you to populate just put in the initial weights and biases, but you're right, you probably could just do it in a single line. Because I think you can create an empty dictionary and then put the right pieces into it.
I mean, in the line above, I create the dictionary with W1, W1, and set all the inters.
Yeah.
And then I need to populate that. But I mean, I already created the X test and X train, so I could just run a forward propagation step, a forward model
I think
definition.
that's what it has in mind.
Okay.
I think it's so this one, there are some solutions provided. So I'm going to have a quick look at what the solutions suggest. So the solutions have just created an empty dictionary. And then populated it.
So and I've done it in one line. Okay.
You've done it in one line, so
yeah,
it's fine. I mean, it's not very clear, but I think that's what it was getting at.
Okay.
Yeah.
Thank you.
So Omar, you had a question about the previous lecture.
Yes, just about the back propagation section. So just a quick clarification is back propagation means just deriving the cost function, the derivative of the cost function.
So
is that
I probably should have gone into a little bit more detail here. I've kind of given the high level view of what's happening in back propagation without giving you the gory details, because writing all the maths makes it look quite messy. But what the idea is that to go from the last slide of the forward propagation, what we have to do during the back propagation is calculate the derivatives of the loss function. Because once you've calculated the derivatives of the loss function, you can then put that into one step of the gradient descent algorithm. So the backward propagation is kind of preparation for doing the running gradient descent. And what we need for gradient descent are the derivatives of the loss function with respect to the weights. So we need to get d loss by d weight for all of the weights going right back to the start of the neural network. And the way we do this is we first of all calculate the partial derivative with respect to the first weight, and then the next one will be a product of the partial derivative at the previous step. So we calculate a new derivative and multiply it by the derivative that we've already calculated. So to calculate dj by so this to calculate something further back, we have to do all the previous steps and multiply them together. So I wonder if I've got a better slide for back propagation just to show the actual back propagation calculation. That doesn't really help. I don't have an obvious slide. So the idea, it really does get quite messy because you've got lots of derivatives as you work your way back. But the idea is that during back propagation, you first of all calculate the derivative of the loss function with respect to the weights in this layer. Once you've done that, you can then see how the weights in this layer relate to the weights in this layer because of this function that you know. So by the chain rule, you can then work out the derivatives of the loss function with respect to these weights, and you work your way back through at each stage using the chain rule. So in the practical 8, where is it? We do the back propagation. Let's see if this, I'm just going to look at the solution one. So gradient, so we do the forward propagation. And so this is the backward propagation here, where we're looking at the rate of change of the weights with respect to the previous one. So this is all sort of so you find the derivative of d weight 2, and we do that by calculating the derivative based on the difference between the output and the predicted values and the actual values to give you the delta, and then multiplying that by the transpose of A2. So that's probably why that's not really obvious. So
I kind of get it. So generally doing backpropagation is doing a kind of a chain of derivatives, so you know how much each input affects the loss function of the output.
yeah, that's what I'm trying to get across at this
Yeah.
level. It's a few.
But of course, there's probably a bit more to that. But
well, no, I mean that's the most important thing. The detail is just in the maths of how you implement that. But the most important thing is exactly that at each stage you need the derivative of the previous layer. So you have to go back layer by layer, and each derivative is based on the derivative of the one before. So like in order to work out D1, I need delta 2, and to calculate delta 2, I need the weights at the previous level. I'm just trying to work out to trace it back. But yeah, it's this idea that you have to go forwards to calculate the predicted value, and then backwards to calculate all the derivatives. And you keep all, and once you have all the derivatives, you can put it back into the gradient descent algorithm, or whichever algorithm that uses those derivatives. Do one step of that to update the weights, and then repeat. So that's the main point that I'm trying to get across.
yeah,
And I've probably
makes sense.
glossed over the maths a bit too much here. I should have been a little bit more explicit about it.
That's fine.
But that's what I was trying to show, what's going on.
Thank you, appreciate
it. So John, I've seen your question about practical 9b. I'm going to pick that up in a bit. when we get on to the last practical session. Or maybe Robert, I don't know if you're here at the moment. If Robert's online, maybe he could make a comment on that. Stephanie, you had a question?
Yeah, back to the 8B session. There is this, when you start training your model in Now Run the Training, they train on X and Y. And I was wondering why they do that, or if it's just a mistake, because we usually run on the test training and then we have the test data, which we have split
You're
before.
right. You're quite right. I think that's a mistake. X is X, Y is Y, and going, unless we've already changed what the definition of X.
No, they haven't, because they still go by the 500 sample set that they have created.
Yeah,
And they've
you're
split
quite
it
right.
before.
You should only be training on the training set.
Okay, thank you.
That's a good point. Okay, I'm going to give the last lecture now. Wait a minute, what's the time? Yeah, so how are we doing for time? So yeah, I'll give the last lecture, then we'll break for lunch, and then we'll go over the last practical using PyTorch this afternoon. So lecture more advanced neural networks. Let me bring up the right one. Okay, so let's carry on from where we were before. So I talked about, so probably the first step up from a simple feed-forward neural network. They're sometimes called feed-forward neural networks as opposed to ones, even to ones which have backward connections in them, which are not feed-forward networks. So the simplest kind of neural networks, fully connected feed-forward neural network. Let's now look at a variation which was designed to deal with image classification. So convolutional neural networks, they're a specific type of neural network. And actually the popularity and success of most of deep learning owes a lot to these convolutional neural networks. They were one of the earliest big advances made once we had enough computational power to do deep learning. So CNNs learn models which recognize objects in images and perform image classification. So there are two slightly different tasks there. One is, can you sort of find the bounding box of certain objects in the image, or can you classify this image? Can you tell me whether it's a dog or a cat? So both of those problems can be addressed with CNNs. And the idea here is that we learn directly from the images. What we have in these CNNs is some very large layers. So the input layer is large. We have one input for each pixel in the image. So we just throw the raw pixels into the neural network. But in this case, the neurons in one layer are not fully connected to all the neurons in the next layer. So I'll talk a little bit about what we do instead in a moment. The final output is reduced to a single vector of probability scores of all the different possible classes that you could have for image classification. Slightly different for object recognition within an image, but we'll focus really here on image classification. These CNNs are often illustrated and modeled in 3D. So instead of having a vector of neurons, a single column of circles, they're often shown as a layer within a layer, a sort of a flat plane, as I'll show you in a minute. You can, from a computational point of view, what happens in the calculation is just that these layers are effectively split up into one long vector, but they're often depicted because they look more like images that way as two-dimensional things. So the CNNs have two key components: hidden layers, which do feature extraction automatically, and they do that with convolution and pooling operations, which I'll explain. And then there's a final bit with fully connected layers, which is ultimately the bit that does the classification. So CNNs are just deep neural networks with particular kinds of layers which have a certain kind of connectivity to the previous layers and a particular kind of activation function which is designed to help identify features in images. So I've said that there are the two most important kinds of layers that you get in a CNN are either a convolution layers, that's the C in CNN, and pooling layers. So what we do in convolution, I should really have got some examples before all these words, but let's go over the words and then you'll see some examples of it. So convolution is the idea of using different filters or kernels on the input data to produce what's called a feature or an activation map. Each filter corresponds to something called a receptive field. And after you perform several convolutions, there can be hundreds of hidden layers in these CNNs, each with a different filter. We obtain a map of all the features, which is the final output. So how you train these CNNs, it's the same as for regular CNNs using backward propagation and gradient descent. It's slightly more complicated due to the convolutional operations, the things that happen between the different layers. So the functions are slightly different, the way you calculate one layer from the next. But the idea of doing backward propagation with gradient is exactly the same. So one thing that you can do manually, even if you don't use neural networks, is to run edge detection algorithms on images. So the way you can do that is to take your initial image and to run a filter over it, which I'll show you the filter in a minute, and the output that you get are, you can pick out the vertical images. It's not particularly clear in this slide here. Or you can pick out the horizontal images. So hopefully you can just see the slightly lighter bar at the top of the fence is being picked out. So this very simple example here is effectively picking out a feature which is vertical lines and another feature which is horizontal lines. So we start by taking an image. We'll use this example and you represent the image in grayscale at the moment. So one channel, we just mean grayscale image, and we use numbers to represent the brightness of the different pixels. So how do we do edge detection? Well, we come up with some. So this is the image that we start with, and then we have to take some kind of filter or kernel and convolve it with the original image. So this operation here represents convolution. I'll show what that means in practice in a moment. And what this does is you move this, when you calculate this convolution, you get something that is smaller than your original image. You'll see why in a moment. Notice that this filter has been chosen and we've got ones here and negative ones here, and this is a filter which will pick out the vertical edges the way it's been arranged here. So what does this convolution operator actually mean? So it means that we go over and start putting this filter in the top corner. I've written the numbers here in pink in the top corner. So we take the filter and we apply it to this part of the image, and we just do matrix multiplication of, we just do straightforward element-wise multiplication of the value of the brightness of the pixel and the number in the filter. So 6 times 1 plus 3 times 0 plus 0 times minus 1 plus 3 times 1 plus 1 times 0 plus 6 times minus 1. And we do that for everything, add up these 9 terms, we get the value 1, and we put that in the top left part of the output image. And then we do the same thing again. We move the filter along by 1 pixel, and we recalculate the same thing. So the same filter, different part of the input image, we come out with a number, and we put that here as the second element in the output. And what this does is effectively highlight those parts of the image where there are edges. So we can pick different kinds of filter to detect horizontal or vertical edges. And then the higher magnitude values in the output matrix, so it could be either positive or negative, they show the areas where the edges have been detected in the image. So we're not doing any neural networks here. This is old-fashioned edge detection by by convolving an image with a filter. So for vertical edge detection, these are the kind of filters that are sometimes used. That's the one we just saw in the example. This is another one that's often used. Horizontal edge detection, similarly, the same thing flipped by 90 degrees. So you can try that kind of operation, or write some code to look for edge detection in images, and you'll see that it works fairly well. The key thing about so what we're doing in a convolutional neural network is that we don't decide what the numbers in our kernel should be. We let these be weights in our model, and then we just let the model find the weights by using the training data and doing forward and backward propagation. So we're not explicitly telling, again, our model is not, we're not providing a model to say you've got to look for certain kinds of features in the image, which are horizontal lines and vertical lines. We just say, look for some features. And it turns out that this works quite well. And as you move through the different layers of the network, you start to pick out more and more complex features. So towards the input side of the network, you really are just picking out things like edges. And as you move through, you can build up more complicated structures, maybe shapes made up of those edges, or things that become more identifiable as features in the images. Question.
I'm just wondering if I break it down, going back from the idea of having it as weights and going back to the filters that we apply, can I say that each hidden layer would be one filter, or is it kind of mixed all over?
So each hidden layer corresponds to, each hidden layer is going to apply one filter, essentially. Each hidden layer corresponds to one filter, yes.
Thank you.
So what happens actually when you transfer this to a network is that if we were going from a layer that had this image to the filtered layer where we had a slightly smaller one, this corresponds in the network to something which was 7 times 7, 47 nodes in a row here in this layer, and the next layer has 5 by 5 is 25 nodes in it, and the value, remember, to get the top left part of this layer, we only looked at 9 of the pixels in the previous layer. So this is a slight simplification of this image because we're only showing 3 of those neighbors. This one is also connected to ones further down and further up, but in total it's connected to just the 9 nodes that correspond to the pixels in the previous layer. So it's no longer fully connected. Every node in the green layer is connected to exactly 9, because our filter is 3 by 3, it's connected to 9 nodes in the previous layer. And the weights on those edges that it uses to connect correspond to the values that will go into the filter. So every neuron is only affected by a limited input, which is sometimes called the receptive field. So 3 in this case. Another thing that's sometimes done in CNN is that some of the parameters, the weights of these edges are tied across multiple neurons. So, in fact, this is often done in CNNs. So you'll notice that we said that there were 9 edges corresponding to the values of the filter. We were trying to find the values of the filter, but we've got one filter corresponding to the whole layer. So this value here basically is going to be the same as this value here. It's going to be the same as this value here. So unlike the simple case where we just allow every edge to be independent, in this case, we force the edges to remain tied, so they have the same values. So we're trying to identify basically a single filter. Sure. Yeah. Question?
Are these filters how like image compression works as well? It feels kind of similar. Like you're getting a 3 by 3 grid in this case, and kind of getting the information from it simplified in a way.
Yeah, it is simplified. In fact, the image compression is maybe possibly closer to the pooling layers that we'll come on to in a moment. But it is exactly the same idea that what is compression effectively doing? You're trying to maintain the important information about the image in a smaller number of bytes. So you're trying to capture the important features of that image. And this is what the models are trying to do, is to sort of pick out the features of the image. So the filters and convolution and so on is very similar to what happens in image compression and things like that. Stephanie?
So by binding the weights together and saying like every downwards line is the same, why do you span up the neural network that large instead of just saying, okay, I use every set of 9 pixels from my picture as an individual input and then have a smaller convolutional neural network?
It's a good question, and I don't know if I can give you a deep answer to this, but what happens, because although these weights are the same repeatedly, the value of this one in this layer kind of comes from these 3 pixels and 6 pixels elsewhere. And this one comes from a different set of 9 in the previous layer, and this one comes from a different set of 9 in the previous layer. So we're trying to keep as much information as we can about all the different areas of the image. So we still need as many neurons in this layer.
So because we combine them in a different way in the next layer, we need this. So unless we...
Yeah. So
okay.
We sort of need to keep the local information,
yeah,
by repeating it. So we're saying, so what are we? So effectively, what we're doing by tying the weights, we're saying we're looking for particular kinds of filter. By fixing the filter, we're saying we're looking for the same features everywhere in the image.
Mm-hmm.
So that kind of corresponds to the fact that at least earlier in the neural network, an eye, for example, in one part of the image carries the same importance as there being an eye somewhere else in the image. What it's doing at this stage is just looking for eyes, or looking for squares, or looking for headlights or something. And then later on, the further down the network, it starts to look at how those are grouped together. So in some ways, it shouldn't matter where in the image a certain feature shows up, at least for the simple features. That is kind of in practice what it's saying, that we're kind of looking for a feature anywhere.
Mm-hmm.
So we need to keep all of the possible, we need to keep the spatial information, but it's the same feature. We don't care where it is in the image, so we tie the weights.
Mm-hmm.
So weights and biases are usually the same for all neurons in a given layer. That means that the hidden neurons detect the same hidden feature, like an edge, in different regions of the image. This is kind of what I've just been saying. So this makes the network tolerant with regard to translations of images in an image. It doesn't matter where the object is in the image. So what we've looked at so far have been black and white images, but exactly the same thing. Color images are just treated as multiple layers. But you'll see that the filter, this front layer of the filter here in yellow, is only doing its work on the red layer. This other bit of the filter is doing its work on the green layer. So it's still working in layers, but we just split those off into multiple channels. And at the end, though, this is flattened down to something that is a single layer. Basically, you do each layer first and then kind of add them together. I'm just trying to see what this bottom picture is meant to depict. What do I want you to take from this? I want you to take from this that the idea of doing it with color images is basically exactly the same, but you can reduce a little bit of the work. The details are in the math. You can reduce a little bit of the work because in the same way that we look for the same, that we bind weights together, we're looking for the same kind of things in the different color layers often. Whenever we do this kind of convolution, we always end up with an output layer that is smaller than the input layer. And as you go through a network, therefore, you might imagine the layers sort of shrink and shrink and shrink, which isn't actually always what you want. So there's a fairly basic solution to this, which is to pad your input values, often with zeros, before you do the convolution. And by doing that, you end up with an output that is the same size as the input. So that's a fairly common thing that is done as well. So rather than the output getting smaller as you go through the neural network, the padding means that it stays the same size. Sometimes we want to reduce the size of the layers as we go through. And so this is the bit that I was saying was a little bit similar to image compression. Sometimes you only want to capture the important high-level information about a certain part of the image without worrying about the detail. And that's what these pooling layers are designed to do. So pooling operation is just a way of taking a grid and coming up with a smaller grid. In this case, it's taking the numbers in the top left-hand corner and coming up with a number here. In this case, it's taking the numbers in the bottom left-hand corner and putting them here. These ones go to here, these ones go to here. This is an example of max pooling. So we're not even taking an average. We're just picking the maximum value that appears in this corner and carry it over to here. 2 is the maximum value, so it goes here. 6 is the maximum value, so it goes here. So this is called max pooling and is quite common as a strategy. The idea behind it, sort of again, is that it's designed to, if you've got high numbers in a particular part of an image, that corresponds to the presence of a feature. So we don't really care whether that feature is in multiple places, or all we want to make sure is that in our reduced piece of information, we still want to make it clear that there is a feature somewhere in that part of the image. So there's other things that people do with the CNNs. They change the stride. That's just the size of the step that the convolution filter moves each time. So usually, and in the example that we've given, this, the convolution moves a single pixel by a single pixel, but you can reduce the amount of work that you have to do by increasing that stride. So sometimes we get examples of layers that have a stride greater than 1. Usually only 1 or 2 normally the more you increase the stride, it decreases the accuracy. It's again a sort of trade-off played between computational effort and the final accuracy. People can change the padding. So I think we've talked about that. And pooling makes the model invariant to small local translations of input. So we get different kinds. We get the max that we just saw an example of, which introduces some non-linearity and greater translational invariance. But you also see average pooling as well. By reducing the dimensions of what we're doing in pooling, it reduces the number of parameters that the model needs to learn, and so it speeds up the training time. The same with having a stride greater than 1. Another thing that pooling helps to do is control overfitting. Now, we haven't really talked about the details of fitting for neural networks, but we did talk about it briefly at the end of the classification lecture, where you could come up with a model that too closely represented the training data and does not generalize well. So as you're training the neural network, you can calculate a training accuracy, which is sort of how well it does at predicting using just the training set. And of course, once you've finished training your neural network, then you can apply it to the test set and see how accurate it was. But if you have a case where you've got high training accuracy but low test set accuracy, they're the symptoms of overfitting. And one of the things that pooling was designed to do was to reduce this overfitting. You can sort of see why it would work, blurring out the points in the linear regression graph a little bit. You could imagine that the model tended to move towards the average of those points rather than trying to fit to every single individual point. Often you get pooling layers interleaved with convolution or ReLU layers, so convolution or activation function layers. But you normally see less pooling than you do convolution layers and ReLU layers. I think that the max pooling is a pretty obvious example here. It's the same kind of thing as, again, that we just take all of these values. The highest one there is 7, so it ends up here, 7. So after we've done the convolution and pooling layers, and these are often interleaved, so you have several convolution layers, then a pooling layer, then several convolution layers. Normally at the end then of the neural network, there would be a few fully connected layers whose job is to do the thing, the classification part. So the first part of the neural network is effectively picking out the interesting features, and then the last part of the neural network is classifying the image as a whole based on the features that it has found in the image. So these fully connected layers are effectively the same as one-dimensional things that we had in the images that we do before. So in practice, what you often see, even in cases like TensorFlow, which is designed for well, one of the things it does is image classification, and it internally stores like an image as an array as it goes through. But at the last step, you have to flatten it to do the classification layer. This fully connected layer is actually where most of the parameters are, because if you have two fully connected layers which have the order of 4,000 hidden units, which isn't that unusual for image classification networks, that means that you've already got 16 million weights in your fully connected layers at the end. Convolutional layers, what does it mean by have more activations? I mean, there are more computation time is put into doing the activation functions, or the functions required to do the convolution. But the sheer number of weights means that most of the a lot of the work, it ends up being done for this classification layer at the end. So maybe I should have started with this, I don't know, but this is an example of a full CNN architecture. This is something called VGG16. When you're using frameworks like PyTorch, there are existing architectures that you can use as a starting point that have been widely used by others in the past. VGG16 is one of the examples of these, and this is what it looks like. So we've got an input image that goes into 2 convolution layers followed by a max pooling layer, and then 2 convolution layers followed by a max pooling layer, then 3 convolution layers followed by a max pooling layer. A lot of these have been Y2 and then 3. These architectures have kind of been arrived at by trial and error, by comparing and using sort of heuristics as to what to expect. You know, do we need more pooling, or do we need more features, or people have some sort of feel for it as they're pulling these things together. But often they've been constructed through trial and error, trying different things to get the best balance of accuracy and runtime. So yeah, after these convolution blocks, which have convolution and max pooling in them, then we get a flatten layer, which just takes the sort of 2-dimensional grid and puts it into one long vector. And then dense just means fully connected. So this is the fully connected part of the classifier, and at the end, and sometimes between these layers, they also put in things that are called dropout layers. Dropout layers are places where you just set some of the values to 0 deliberately, and you can do that in a sort of controlled way. You can decide how much of the signal you want to drop out as you go through the network, and again, that can help with overfitting so that you can get a more generalizable model out at the end. So this architecture was the winner of, they have competitions designed for given sets of input data that have already been labeled, for example. How well can you, what's the best accuracy you can get? So this is in this competition, what's the best accuracy you can get on ImageNet, which is this large curated set of images used for image classification for training. And this particular architecture was the winner there. So again, so frameworks like PyTorch and TensorFlow, as well as providing these architectures ready for you to use, in some cases they also provide you with pre-trained models. So you get the architecture that's already been trained on ImageNet, which means that you can just apply that. You can either just take that model out of the box and apply it to some new images that you've got if you're trying to classify the same kind of images that were in ImageNet, or you can use transfer learning that I mentioned earlier to start from that pre-trained model and train it on some different kind of input data for your particular problem. So the frameworks, as well as implementing things like forward and backward propagation, they also provide example architectures, and they also provide pre-trained models in some cases as well. So dropout, yeah, these are units or neurons that are during the training phase. You just do not consider those neurons during a particular forward or backward propagation. They're chosen at random, and you do this to avoid overfitting. They're often used between fully connected layers of the classification part to improve the generalization error. Yes, so most of the models, it's not really about the underlying hardware that's made them. So when I talk about cost to performance, a lot of people, the time to do a single or forward or backward propagation tends to be fairly fixed. So when people talk about performance, they often talk about epochs. So rather than actually saying that you need a number of seconds to run or minutes to run the training, people often say that, oh, you need to run it for 100 epochs or something, which means that you need to use all of the training data 100 times, pass all of your training data through the network 100 times in order to complete the training. And on one architecture, on one computer, one piece of hardware, an epoch might take a certain amount of time. On another architecture, an epoch might take a different amount of time. But generally speaking, the underlying hardware will not, it won't change the number of epochs that you need for convergence, or the kind of accuracy you get from a certain number of epochs. So performance is often about the accuracy you can get for the number of times that you have to pass the data through the network. And then there's the second question then of, okay, what's the best kind of hardware that I need to perform the particular kind of calculations that I need in my forward and backward propagation, which is nearly always matrix multiplication, but some variety of that. What kind of underlying hardware do I need to be able to do that efficiently? And that will control the speed of the epoch. So generally speaking, a particularly successful architecture, or a particularly successful or pre-trained model that's always got some accuracy, they are generally speaking sort of the portable between different hardware in terms of how well they'll perform. Yes, the hardware can matter in terms of, and can matter a lot in terms of how fast you can do the calculations to get your data through the system. But often the performance is, in terms of how many epochs it takes to train a model, that will be the same on different architectures. So residual networks and depth, increasing so the different people over time. I mean, the history of neural networks is mostly about people trying to increase accuracy and decrease runtime. So increasing network depth, this is a way of increasing the accuracy. In practice, and some people have put forward ideas for why this might be the case, but I don't think it's widely acknowledge that there is a specific reason for this, but generally speaking, going longer gives you better performance than going wider, making bigger layers with the same number of parameters. The longer you make the deeper you make your network, the more there is a risk of the vanishing gradient problem, which I've mentioned but not really talked about in detail. But sometimes when your derivatives get very close to zero or very high, it makes the propagation, the calculation, very difficult from a computational point of view. So although you can start to get increased accuracy, it can be harder sometimes for these to converge because of vanishing gradients. So part of this vanishing gradient problem is one of the reasons why sometimes they put these skip connections in the residual neural networks to allow gradients to be accurately propagated, or some non-zero gradient to be propagated back successfully through a deep model. So yeah, a little bit more detail, skip connections. This is an example of another network called ResNet that you sometimes read about in the literature. Again, it's a particular architecture. What they do, you can see pooling layers and convolution layers here again, but they also have these skip connections between some of the layers, which aims to avoid these problem of vanishing gradients as it gets deeper. So inputs with more complex structures will travel across more connections, so all relevant features can be covered. Yeah, it's a bit harder to kind of picture this, but that's the kind of rationale for why these things were introduced. This only goes up to 2016, but it shows some of the history of how these things have developed over time. So back in 2011, this was the kind of era we were getting on. So this is the same classic ImageNet test set that are used in the competitions. So back in 2011, there was an era of 26. As time went on, this one, 2014, had 19 layers. Then this LENet or GoogleNet from Google did better on ImageNet by hanging up to 22 layers. Interestingly, about this point, it started to beat what some human classifiers would do on the image set. So this is a little bit hard to measure because you've got to be a little bit careful about how the images were originally labeled in the first place, because they were probably originally labeled by humans. But you can imagine this as being a single human compared with a curated, tested, labeled test set that's maybe been evaluated by multiple people at multiple times or something. So anyway, the key point here is that around about 2015, some of these classification algorithms A, got very big, but B, were able to beat humans for the first time in terms of how well they could classify things. And it has continued to improve since 2016. I must try and find an up-to-date version of this. So some popular architectures that are out there: ResNet, that's the residual network with links to skip layers. There's something called Inception Network. What they do is they combine multiple filters and then allow the network to learn the best filter to use. So that sort of simultaneously, the normal way of doing it is to have a single layer representing a single filter that we've talked about. The inception network kind of carries multiple versions of the filters through, and then allows the network to find the one that works best. Mobile net is another popular architecture. That was an attempt to lower computation cost using a lower dimensional filter. Efficient net included features to trade off resolution, depth, and width to get the best results with smaller computational resources again. And these are some of the earlier ones that you'll probably see in the literature. One last little point, just because I promised to get there. Some of the most recent neural networks that have come about are these transformer networks, the ones used in ChatGPT and so on. Whereas most of the evolution that I've talked about here was driven with image tasks in mind. A lot of the recent developments have been driven by natural language processing tasks. So coming up with writing written answers, automated chatbot type things, and other natural language processing tasks. So originally with natural language processing, the technique was to use bag of words, where you just had a vector of length n to represent the words. And you can do basic document classification with this approach. So that was kind of the simple classification algorithms that we had the other day. You don't even need to do neural networks. You just have to have some way of representing the words with a distance function. So that was the original approach. The issue with bag of words, kind of is that these don't really take order of the words into account. So the recurrent neural networks were the first attempt to get around this. So this is with backward links in the networks, so that it could have memory of previous words being fed back in as it calculates things for subsequent words. So that was an improvement in that it had some memory, so it could take order of words into account. Unfortunately, the vanishing and exploding gradients are a big problem with RNNs. So in 1997, the LSTM models were proposed. That stands for long short-term memory. It's a way of another way of better capturing memory by using gates, essentially, so that some information is retained, but you also don't let some of the gradients that are likely to vanish or explode back propagate through the network. So by gate, I mean so other parts of the network actually don't pass a gradient. It sets something to 0 when it would otherwise vanish or explode, for example. So that improved the memory and improved the vanishing and exploding gradients, but they're still difficult to train. They proved bad for transfer learning, the idea of taking one model and applying it to a different related data set. It didn't seem to work very well with LSTM. And the other problem with the LSTM architecture is that it's inherently a sequential calculation, because everything, the backward links are things that you have to do in a certain order, so it takes a very long time to calculate. The advantage of transformers, which came on next, and instead of the key sort of vision here, built on the idea of gates, is the attention mechanism. And so these transformers use something called self-attention. And this is basically a way of saying which parts of the information do I want to be, which parts of the information coming through the network do I want to keep paying attention to. The networks come up with ways of doing that with certain interconnections between the layers. The great advantage of transformers is they can process data in parallel. So you can do a lot. If you've got a very big machine, whether that's a supercomputer or many machines in the cluster or the cloud or something, you can do the learning process. It scales very well. So it still requires a lot of computational power, but you can do it more quickly because you can just throw more machines at it. They appear to give better results than LSTM, and in particular in terms of they're better at keeping track of context, which is sort of why ChatGPT appears to give such coherent answers. It probably explains the fact that the words that you get out are very, they appear to make a lot of sense, even if they're not always 100% accurate in some context. Even when ChatGPT lies to you, it lies to you in pretty good English because it's good at keeping track of the words that it's already used. So that's kind of how things have developed more recently, and these are the different kinds of architectures. But most of the changes are to do with sort of how you calculate one layer from the next, whether there are backward links. But again, throughout all of these, the idea of forward and backward propagation to find the values and backward propagation to find the gradients is conceptually identical, even in these different architectures. So you've just got to learn the details now if you want to build your own ChatGPT. So neural networks, highly parameterized, nonlinear models where the parameters, the weights and biases, are calculated using backpropagation to calculate gradients, which are in turn used to minimize a loss function. Increasing depth gives more parameters, which tends to allow for a more accurate model, but it can risk overfitting and it can be computationally costly. The architecture itself is often selected for the problem at hand, but often this boils down to the way of finding different ways to try to optimally trade off accuracy, training time and convergence, and prediction time. Okay, so apologies for running slightly over the timetable, but I just wanted to get to that point where at least you can see, if not the details of how something like ChatGPT exists, but what of where it comes from and where it fits into the history of the development of neural networks. So let's break for lunch now. Slightly late, apologies. Let's reconvene at, let's say, 1:40. I'll be back at 1:40 anyway. You can take a bit longer if you need to. And that'll give you a chance to work through the last bit of practical using PyTorch, hopefully. And then we can wrap up after that. And I'll probably be around for questions till about 3:30. So yeah, let's break now until 1:40, and then we can reconvene, and I can take any questions that you have at that point. And I can go and charge my computer before it gets too upset. All right. Speak to you soon.